Hi folks. So today we shall look at a very interesting and very easy concept. Okay, it's in geometry, it's on circles. Now, geometry is very interesting because it's very intuitive. You see shapes all around, you can touch and feel them, you can visualize their properties, right? So this is one of the most easiest chapter in grade 9. So let's get into it. So today's agenda, we look at, what a circle actually is, what are its parts like the circumference, arc, chord, tangent, secant, sector, segment, and all that is needed for us to appreciate the theorems we are going to learn about circles. Okay. And definitely we are going to look at polygons that fit inside a circle and polygons that contain a circle within them. Okay. All of these are prerequisites to not only apply, but to prove the theorems that we have on circles. Okay. Cool. Moving on, I think circle is a perfectly symmetrical shape, right? When you look around, even as a child, when you look at planets, when you play with a ball, it's all, it's it's this perfect mystery shape that we have. And if you've ever played with this tool, I don't know how many of you in your childhood have tried this. There is this set of tools that you place one shape into another and you start drawing patterns like this, right? The beautiful patterns. And the thing is, you repeat these patterns, they're all confined within the boundary of the circle, and you get wonderful shapes like this. These are called spirographs, okay? Not only that, if during the lockdown, if you've, uh, you know, you've started this hobby of mandala drawing or any such drawing, then you'll realize when you get a color book and you paint the mandala itself, a shape like this, is actually obtained by drawing these concentric circles, right, guys? So circles are very intriguing. And anytime you sit and observe a circle or any shape that's inside a circle, you can build symmetrical shapes, infinite symmetrical shapes within a circle. And I think that that's what is very interesting to us. And circle as a shape has been very interesting to mathematicians, philosophers from time immemorial. Cool. So what we'll try and do is spend some time understanding the concepts related to circles and the terminology. So when you start the theorems, there's no ambiguity. You understand the parts, you understand the shapes, and you just, it'll just flow once you know the parts of the circle. Cool. So if I were to ask you what a circle is, right, most of you would fall back to defining a circle as a shape with no edges, right? There are no edges in a circle. It is a perfectly round shape. It's a curve, so on and so forth. But this year, let's try and define it with a bit more detail, okay? And that is, a circle is the locus of points. We'll discuss what this new term means. It's the locus of points on a plane or a surface that are at a certain distance from a central point. Okay, what do we mean by this? Now, the term locus in itself, it just means it's a collection of points that satisfy a certain condition. Okay, so let's say I start with a fixed point somewhere here. You all know in geometry, a point is not a dot, right? It's not a filled circle. A point is a location in space, right? Location in space. Okay, so if I begin with a fixed point, let's call this point P, And supposing you imagine you have a small you have put in a small metal rod here on the ground, and you tied a rope to it, and you're holding one end of the rope, and you're just covering, you're kind of walking around this pole. Okay, so if you're covering this equal distance, let this distance be a half a meter. Okay, if you're covering this distance around this fixed pole at every point here, then these collection of points, okay, form a circle. That is exactly what we mean by a locus. So from now on, you'll see in grade 9 and grade 10 that you start defining shapes as a collection of points that satisfy a certain condition or a geometric rule. Cool? So a circle is a locus of points on a plane that are at a certain distance, okay? And this certain distance, you would have figured by now, is the radius of the circle, and this fixed point, okay, is the center of the circle. Cool? So this is a new definition that you have to get used to. And now when we talk about the circle, right, you can't forget pi, right? The beautiful ratio or constant called the pi. So pi, what is pi, guys? I mean, we're not talking about its numerical value here, but pi is ratio of the circumference of a circle to its diameter. Am I right? So this is where you actually derive what the circumference of a circle is. So from this, circumference is pi d, or if you replace the diameter with 2 times the radius, you get circumference as 2 pi r. Okay, and when we spoke about measuring shapes in mensuration, we discussed why the area of the circle is pi r squared, right? We spoke about the method of exhaustion, and we looked at some animations there. So by now you kind of appreciate why the area of a circle is pi r squared. Okay, so keep all this at the back of your mind. We will now look at certain other aspects of a circle. Okay, what is an arc? Okay, so if we have a circle and if I call these points as A and B, then actually AB is an arc. Okay, so an arc is actually part of the circumference of a circle. Right, guys? It's as simple as that. So part of the circumference of a circle. In geometry, whenever you try to draw angles, you bisect an angle, you draw a perpendicular bisector, you all are used to drawing an arc, right? It's actually a part of the circumference. You don't complete the arc, but if you were to complete the arc, you actually end up with a big circle. Cool. So if I asked you what is the biggest arc in the circle, it is the circumference, right? It's the entire boundary or the perimeter of the circle. Now, what is, so you do understand what the arc length is. For this arc AB, this does have a finite length, right? Let's call it X. And there are ways to measure this as a ratio of the circumference. It is some part. Let's figure what that part is. Now, let's say we have a circle with center O here, okay? And we have an arc PQ, right, guys? And if I told you this angle that is formed when I connect the end points of an arc, P and Q, to the center O, then indeed an angle is formed, right? And if this angle is 90 degrees, then you know that this portion is actually called a quadrant. Right, guys? If you split a circle into 4 equal parts, you get a quadrant, and we know that the angle about a point is 360 degrees. So if you split this by 4, you get a 90 degree. Okay. Now, if instead of the arc PQ, I move the point Q around, okay, and I drop it here, right? Then this is a complete, this is a straight angle. It's a 180 degree. And you will see that the arc PR, the length of this arc is going to be half of the circumference. Hold on. Yeah, the length of this arc is half of the circumference, or in other words, right? I just doubled the angle this arc makes at the center from 90 to 180. So you will observe that the length of the arc has also doubled. Instead of being 1/4 of the circumference, it's now become half the circumference. So there is indeed this relationship between the angle that the arc makes at the center and the arc length. Okay, so there is a relationship between the angle subtended. This is a word you start using from now on. The root of this word is basically sub means under, tendered means stretched. So if we have an arc, guys, something like this, I mean, it's not a perfect arc, but let's do a better job at this. Hold on. So let's say I have an arc here, okay? Now this arc, if I can mark a point anywhere. Let this point be Z and let this point be B, okay? Now I have the endpoints of this arc as C and D. If I were to join the endpoints of this arc to a point, arbitrary point C, then of course an angle is made here. Then I can say this angle, okay, let's say this is about 23 degrees. This is the angle subtended by this arc CD on a point C, or if we were to look at the angle subtended by the arc CD at the point B, this measure could be different, right? So an arc technically can subtend an angle at any point. But now, as we speak here, this is the angle subtended by an arc at the center, and it has a special name, okay? And that is called the central angle. Okay, kindly pause and make a note. The central angle is the angle subtended by an arc at the center of the circle. Okay, sometimes throughout this chapter, if you don't use the word central angle, you can still assume that it is the angle subtended by the arc at the center, okay, in this chapter, not elsewhere. So this is just to let you know that an angle can be subtended by an arc anywhere, but if it does subtend an angle at the center, then that is called the central angle. Okay, guys? And we also saw that the arc length, okay, the arc length is proportional, right? It is, if you increase the central angle, the arc length increases. So the arc length is proportional to its central angle, right? We will also look at the formula to arrive at the arc length in the next video. But for now, we just have to appreciate what an arc is, what is the arc length, and what is its central angle. Fantastic. Okay. Now I want you to also extend this concept and think about this scenario. Let's say we have two concentric circles, right? The smaller circle is of radius small r. The larger circle has a radius capital R. Now, if this is the arc PQ made on the smaller circle, and let's extend this line, straight line, okay, which is also the capital R, and I'll call this arc AB. So guys, I want you to think, what is this central angle theta, okay, that the arc PQ extends on the smaller circle, and the angle that the arc AB extends at the center of the circle. Okay, now you'll observe that yes, indeed the angle is the same, because when you have two lines that meet at a point, right, the angle is a measure of rotation of this line about one of its endpoint. That is how you actually define an angle. So, you know, if this is 30, obviously at anywhere else, it's the same angle between the two lines. So the central angle of arcs PQ and AB is the same. It is theta. Now you will have to pause and think, then what can you say about the arc lengths PQ and AB? Okay, what are they related to? Okay, if you pause and think, you will come to a conclusion that in this case, look, if the central angle is the same, then the arc length is just proportional to the radius, the ratio of this radius R and R. Okay, so we'll come back to this when we study in detail about concentric circles, but I just want you to appreciate the fact that there is a lot of relationship between the central angle, arc length, the radii of the radius of the circle where this arc is drawn. Okay, cool. Moving on. So let's say there is a line, right? Now a line extends infinitely in both directions, right? We have a line and then we have a circle. So there are various options, guys. The line can intersect the circle, right? Like this, as it's shown. So let's say this line is touching the circle at points A and B. Okay. It could also intersect the circle at this point. And as you keep moving this line down, there comes a point where it touches the circle only at one point. And eventually, if you move it further down, now there is, the circle and the line just don't intersect, right? So if you look at this line, I'll call this line L1. Okay, I'll call this line L2. All these lines are called secants, okay? So a secant is a line that touches the circle, that touches the circumference of the circle at 2 points. Okay? Bear in mind when we use the word line, right? This extends infinitely in both directions, okay? In other words, this is not a line segment, it's a line. And this special line out here, line L5, the line that touches the circle at only one point is called a tangent. Cool? So a line that touches the circle, touches a circle at only one point is called a tangent, okay? And for the line L5, this point, there's a special name for this, okay? This point where it actually touches the circle is called the point of contact. Okay, point of contact for the tangent. Okay, we'll also study a few properties of tangents. Good. Okay, so I hope so far you are drawing circles, you're making a note, because these are new concepts that you're learning. Fantastic. Moving on. Now let's talk about a chord. Okay. In the previous slide, we spoke about a secant, right, guys? So this line is a secant. Now, if I look at the secant and actually chop off this portion that extends infinitely, right? We cannot show that it's extending infinitely, hence we use the arrows. But if I were to only consider the portion of the line or the line segment that touches the circle at 2 points, right? Then that becomes a chord. Okay, something like this. So a line segment that touches the circle at 2 points. The only difference between a secant and a chord is that one is a line and the other is a line segment. Please make a note. Okay, is called a chord. So as you can see, you can have infinite chords in a circle. Am I right, guys? This is a chord. This is a chord, right? This is a chord. And as you can see, chords can intersect, right? In this case, I have chord PQ and RS. They are intersecting inside the circle, right? There are cases where chords may not intersect inside the circle. For example, let's say these two chords, the blue lines, they are parallel and they never intersect. Okay, so in this case, they are called parallel chords, whereas PQ and RS are called intersecting chords, because at the end of the day, they are line segments. They will have properties just like any other line segments. They could be parallel, they could intersect, right, guys? So they could be parallel chords, they could be intersecting chords, so on and so forth, right? Another thing is, let's talk about equal chords, okay? Supposing I have this chord here and let's say it measures 7 centimeters, right? Then, oops, hold on, 7 centimeter. So where else do you think you can find another chord of the same length? Okay, can you imagine that? So it could be somewhere here, right? 7 centimeter, which is on the opposite side, and something tells you, look, they may be parallel, right? Or it's not necessary that for equal chords they have to be parallel, not necessary. Observe something here. Supposing I have a chord of 4 centimeter, I could still have two chords that are not parallel. Imagine both of these are 4 centimeters each, 4 units each. Then it's not necessary that equal chords need to be parallel. In this case, these two chords are intersecting at a point, but they can also be equal in length. Okay, guys? And if I were to ask you what is the largest chord, it is the diameter, obviously, right? Because a diameter also touches, oops, that was a very bad circle. A diameter touches a circle at 2 points. The only difference is the diameter passes through the center, right? So it touches the circle at 2 points and the largest chord is the diameter. Okay? Fantastic. Now, when you think of parallel chords, guys, are you able to arrive at any observation about these parallel chords? Okay, if not, just think about them. And when you're drawing these parallel chords, I want you to take a minute Draw a circle of your own and draw as many parallel chords as possible and arrive at some observations about them. Okay, pause the video if you want to and just try that. So I'll try as we are speaking. I'm drawing another chord here. Of course, it looks like a secant, but let me see if I can chop this portion of the whole circle. The whole line goes, just hang in there. I'll erase this whole thing. Let me draw a chord that is parallel to these two chords. Okay, here's another chord. Here's a chord parallel to the given one. So, do you observe that as you move farther away, let's say this is the diameter, as you move farther away from the center, the chord is getting smaller and smaller, right? Or if let's say I start from here, I start from chord EF. In other words, we can discuss the same thing in a different way. As I get closer and closer to the center, my chords are becoming longer and longer, right guys? Keep these observations and patterns at the back of your mind. We'll apply them when we prove certain theorems. Okay, cool. The next part of a circle is a sector, right? This is something you've actually used, you know. If I just tell you, you will know where you've used it. But the definition of a sector is this, right? You start with a circle, okay? And then you pick an arc of the circle. Let's say the arc is arc AB. Okay, you pick the end points of this arc and connect them to the center O. Then this region that you get, this area that you get is called a sector. Okay, so the actual definition of a sector is the area bound or bounded, okay, the area bounded between an arc, because for a sector, first and foremost, you need an arc, okay? The area bound between an arc and its corresponding radii. Corresponding radii. Why do I use the word corresponding radii? Okay, pay attention. I first drew the arc, I picked an arc, right, AB, and I picked the endpoints of the arc and joined them to the center, by virtue of which I get two radii, and this region that is bound between the radii and the arc is a sector. Now, if I don't use the word the corresponding radii, what's bound to happen? Let's say I pick an arc CD here, okay? If I just say it's an area bound between the arc CD and radii, you know, I don't specify what radii, then it could be even this, any other radii out here, right? This is also a radius, this is also a radius, but then, you know, this region is not the sector. If you pick an arc, you have to pick its radii. That is the radii that you make by picking the endpoints of the arc in question. Okay, so please use this word, the corresponding radii. So this is like a pizza slice or a dosa slice, guys. That is a sector for you. Now, as you can see, when an arc makes a central angle, right? We discussed about arc and angle subtended by an arc at the center. So if you have an arc, you always have a central angle. Similarly, now that you're talking about a sector with respect to its arc, a sector also has its central angle, okay? Now in this case, what we've done is, I had a circle, okay? Right? And I have arc AB, right? Yeah, I forgot to talk about the minor arc and major arc. Right? Now, if you look at AB here, right, this is one arc, it's part of the circumference, and you see when you compare that with the other portion of this arc, that is, if I were to join points A and B in this roundabout way, then this is also an arc, right? But you clearly observe here that this blue line, not the dotted line, but the blue thick, very shabby line that I've drawn here for the arc is longer or is lengthier than the dotted line AB, right? So the smaller one is called as the minor arc and the larger one is called as the major arc. In other words, if I had a circle and I split the circle into two semicircles, then both the arcs are equal in length, right guys? Then there is no concept of major and minor here. Both arcs are equal in length. But if you pick 2 points such that the arc that is formed, right, 2 arcs that are formed, one of them is smaller when compared to the other one and the other is larger. So accordingly, it's called the major arc or minor arc. Clear? And you'll observe a relationship here. Supposing the central angle of major arc is a minor arc AB, the dotted line is 120 degrees, then the central angle of the major arc, which will be this, right, will be 360 minus 120, right? Because the angle about a point is 360, okay? So similarly, going by the same concept, you have, you have a major sector and a minor sector. Okay, so major sector is formed by the major arc and its corresponding radii. The minor sector is formed by a minor arc and its corresponding radii. Okay, and the central angle of a sector is equal to the central angle of the corresponding arc. Easy? Okay, fantastic. Now, let's just erase all of this. Let's observe one thing. So when I said that you already know about this shape called sector, you know, when you study 3D shapes, right? Do you, if I were to pick the sector here, let's say, let's say this is center. Oh, this is PQ. This is a minor sector, by the way. If I took PQ and I join, if I cut this sector on a piece of paper and then I joined PQ, the two ends, right? What do you get? You get a cone. So a cone is actually formed by a circle at the base and the remaining portion is actually a sector. Okay, so the constituents of a cone are a sector and a circle. But yes, bear in mind that the radius of the sector is different from the radius of this base, right? Because you're joining, let's say this is O, this is P and this is Q. This radii could be different from the radius of the base, okay? Fantastic. So moving on, let's talk about the segment. Okay, just like you pick an arc and you join the radii of this arc, you get an area that is sector. For a segment, you start with the chord. Okay, so if you have a chord PQ, the area bounded between a chord and its corresponding arc. Okay, so we have the chord PQ. And we have the arc PQ, right guys? The points are the same, but one is a straight line, a chord is a line segment, an arc is a curve. So this region is called a segment. Okay, so the area bound between a chord PQ and its okay, I don't want to name a chord PQ because let me erase this. Area bound or bounded, right? Sometimes when you talk about the right usage, it could be bounded. Area bounded between a chord and its corresponding arc. That's important, okay? Corresponding arc is called a segment, and as you can see here, a chord splits a circle into two regions, And one region is definitely smaller than the other unless it's a semicircle, okay? So the smaller region is called, this is the smaller region, it's called the minor segment, right? And in this case, this area, which I've indicated with dots, okay, the filled in area here, this is a major segment. So as you can see, whenever you have a chord and its minor arc gives you minor segment, a chord and the area between a chord and its major arc gives you the major segment. Clear, guys? Okay, so here's just a the shaded portion. So in this case, if we chop this guy off, you're left with a major segment. Okay, major segment. So these are the various parts of a circle. Okay, now let's also study a bit about inscribed and circumscribed polygons. Okay? What do we mean by polygons? I think you've studied a lot about polygons. These are closed figures, closed shapes, whose sides, the number of sides are greater than or equal to 3. Right, guys? So here you'll see that I have a triangle. I have a triangle ABC that is placed inside a circle such that all the vertices of the triangle lie on the circumference of the circle. Okay, so I think you know about this. With respect to triangle ABC, you call this circle a circumcircle. Am I right? It's called the circumcircle. What you're actually doing is fitting one shape into another. You're trying to fit a polygon into a circle. This has a special name, it's a circumcircle. Similarly, you can fit in a quadrilateral inside a circle. You can fit in, how many sides is this? 1, 2, 3, 4, 5, 6, 7. A septagon inside a circle. And also, guys, these can be irregular polygons or regular polygons. We don't care as long as the vertices fit, or the vertices, all the vertices of a polygon are on the circumference of the same circle. Okay, then they are called inscribed polygon. Okay. Now, what's the difference between these two shapes that you see here, figure A, figure B, and figure C? In figure C, what's actually happening is we are fitting a circle inside a polygon. It's the other way around, okay? And we call this a circumscribed polygon, which means it's a polygon in which each side of the polygon is a tangent to a circle. Okay, please make a note of these. In this particular chapter, we're going to study in detail about a quadrilateral, which is, a polygon with 4 sides that has its vertices on a circle, and this guy has a special name. It's called a cyclic quadrilateral. Okay, you will see some beautiful properties of cyclic quadrilateral, after we study about the angles that an arc subtends and all of that. Okay, so I think these are the prerequisites, guys. If you've understood all of the concepts well here, then it's going to be very, very easy to learn the theorems. What I request you to do is, after watching this video, make notes and take the assessment in the next part, and then we shall learn the theorems. Thank you.